Monad is extremely focused on optimizing the performance of a layer one blockchain by making fundamental improvements to the execution and consensus stack. The goal is to saturate the capabilities of the hardware and basically make networks that are much more computationally dense so that one blockchain network is offering well over 10,000 transactions per second of throughput or a billion transactions per day. And then at that point, if there's a need for multiple billions of transactions per day, which I do believe will happen at some point, then there's always potential for horizontal scaling for multiple Monad instances that each are processing a billion transactions per day.
The blockchain space is currently witnessing a transformation from single threaded execution environments like EVM to multi threaded execution environments like Solana Virtual Machine and Move Virtual Machine. The recent spike in activity on Solana is a testament to the success of this multi threaded approach. But at the same time, EVM is still the most successful virtual machine in the blockchain space with most developer adoption, the most number of daily active users, and the most TVL. So this is where Monad comes in and takes EVM and converting it into a multi-threaded execution environment, making it more performant and also secure at the same time. So what exactly is the Monad thesis here? So that's why we are having this conversation with Keone Hon, the CEO of Monad Labs, to go into the details of Monad Thesis and understand how Monad is executing this multi-threaded approach with EVM. So without further ado, here's the conversation with Keone Hon. So welcome to the conversation, Keone. Glad to have you here.
Awesome. Yeah. Thank you so much for having me.
I'm so thrilled to have this conversation with you because Monad has definitely captured the imagination of a lot of people in the Web3 space. And before we go into the nitty-gritty details of Monad and how it makes EVM more efficient and faster, I would love to know your story. So could you tell us your story?
Awesome. Yeah. Thank you. Really appreciate that. I'll just give a quick intro. I'm
Yeah.
Keone. My previous background as I don't know, as a high school student was really interested in competition math and um, proving, getting challenged to come up with proofs for various interesting mathematical facts. Studied computer science at MIT and then ended up going into the high frequency trading space. And the cool thing about HFT is that it's just very open ended because there's a ton of data coming back from the exchanges, and you have to kind of corral all of that chaos, like hundreds of millions of packets coming back from the exchange, into actual structure and ultimately into predictive power. So we're trying to predict very short term price changes that are happening. And it's totally open ended. You could take any kind of approach, try any kind of machine learning model or come up with any kind of signal that is trying to, generate signal from the noise. Did that for a number of years, built a really high performance trading system at Jump Trading, where I was a quant and team lead from 2013 until 2021. And then ended up joining the crypto team at Jump and worked on Solana DeFi for a little bit, which kind of brings us to Monad because at Jump Crypto, I think everyone on the team was really excited about Solana, and it made a lot of sense because as high frequency traders, we're sending tens of millions of orders per day to exchanges. So it would be not feasible to run that kind of business model if every single order cost several dollars like it would on Ethereum, or even tens of cents like it does on Ethereum layer twos right now. You
Yeah.
need fractions of a cent transaction fees in order to enable high quality markets with low slippage and tight spreads. And that was really only enabled uniquely on Solana at that point in time. So was part of the team at Jump there, working on Solana DeFi in particular, and just realized that there was a huge need for more performant EVM because the EVM is the common standard for the crypto space. Almost all developers are building for the EVM. They're building in Solidity or Viper or other languages. And I believe about 96% of all capital on chain, all TVL, is in EVM applications. So It's very much the dominant standard, and I just could see that there was a huge need for more performant EVM. So I ended up leaving Jump and starting Monad at the beginning of 2022. And then since then have just been working on building out the technology, which we could talk about in a little bit, and growing with an incredible community that is excited about our vision of making the EVM really performant and very much carrying the banner for Monad and letting everyone else know why it's so important.
So you are using the concepts from Solana and also combining it with Ethereum EVM and building an entirely different blockchain, layer one blockchain. So in that context, why did you try to build a separate L1 rather than try to build in the Ethereum ecosystem, which is huge, the biggest ecosystem actually, there's the biggest mind share and everything. So what was the reason? What was the core reason to build a separate L1?
Yeah, I guess first of all, I would say that Monad very much is still part of the Ethereum ecosystem. Monad is really going down like a depth first search of trying to make execution really performant and doing a lot of low level system engineering to address the bottlenecks in execution, which include moving from single threaded execution to parallel execution, as well as addressing the state access problem, because realistically, one of the biggest bottlenecks for execution is actually pulling state from SSD, making that state access much more performant with a custom database that we've built called MonadDB, as well as other improvements overall that help really streamline the execution of Ethereum smart contracts. So it's a different direction compared to the vertical scaling approach or the fractal scaling approach of layer twos. But I think it's one that's very much needed in the Ethereum ecosystem. We need people going in different directions, exploring in a depth first search way those different directions, going deep and producing meaningful improvements. So I think that although Monad is not a layer two, I think that there is very much a spectrum of different kinds of blockchains and their overall relationship to Ethereum. For example, there's some layer twos that are using Ethereum for data availability. There are other ones that are using Ethereum only for settlement, but not for data availability. And then depending on which DA layer they are using, that there's like differences there. So there's very much a spectrum in terms of the usage of Ethereum for economic security, but then there's also a difference in terms of the degree to which each of these environments is pioneering technological improvements that are beneficial to the entire ecosystem. So I would just push back on the notion of Monad being totally separate from Ethereum because the effort is very much to try to improve and extend the capabilities of Ethereum by doing deep research. But with all that said, the reason why Monad is not a layer two are a couple of things. Number one, decentralization. We think that decentralized block production is extremely important. Having full BFT consensus with hundreds of nodes participating in consensus, producing blocks, that's really important for censorship resistance and overall decentralization. I think a second reason is performance. Monad is just designed to be a really performant system, and we've optimized all layers of the stack, both consensus and execution, in order to enable that, and done that by making software improvements rather than relying on high hardware requirements. So these are fundamental algorithmic improvements that just allow the software to get as much out of the hardware as possible. And then number three, cost, because it's really important for users to be able to interact with a really low cost environment and it enables new use cases that really cannot otherwise exist. For example, if you imagine someone playing RuneScape for an hour and they pick up 50 items over the course of that hour, then in Monad, we expect that each of those transactions will be a tenth of a cent. And so 50 times a tenth of a cent is still 5 cents. So it's okay for someone playing a game to pay 5 cents per hour to play that game. They probably wouldn't directly pay it. Maybe it'd be subsidized by ads or something. But then if each of those item pickups is 10 cents, then 50 times 10 cents is $5. And like $5 to play an hour of RuneScape is not going to be economically sustainable. So there's just a lot of applications as well as a scale of users for mass user adoption where it's really important for those costs to be sufficiently low. And with Monad, we're able to do that through these different algorithmic improvements that we've made.
Could you break down the main optimizations that you brought to the EVM and also to the core architecture of Monad to make it more performant.
Right. So just to summarize really briefly, Monad is a fully bytecode equivalent EVM layer 1 with over 10,000 transactions per second of throughput, 1 second block times, and single slot finality. And the full bytecode EVM compatibility means that any application that's built on Ethereum can be transported to Monad and redeployed without any code changes. That's really important because developers um, don't want there to be any even subtle differences in terms of the bytecode behavior, because then that will trigger a re-audit because you don't want any possible changes that might create a security issue. Monad is able to do that through algorithmic improvements rather than by relying on high hardware requirements. And there are 4 major improvements. Those 4 improvements are number 1, parallel execution. Number 2, a custom state database called MonadDB. Number 3, asynchronous execution. And number 4, a high performance consensus mechanism, which we call Monad BFT, which is pipelined 2-phase hot stuff consensus. And I'll talk about each of those, but I just wanted to give that as a high level overview. 4 major improvements. Now to talk a little bit more about each one of those. Parallel execution. I think this is an area that Monad is really known for because we're helping to move the Ethereum Virtual Machine from single-threaded to multi-threaded. Just as in modern computers, since a long time ago, we've gone from just a single-threaded computer to multiple-threaded, multiple processor computers that can do many things in parallel. And I think everyone intuitively understands why parallelism would be a speed up. But I think the thing to highlight in particular is that this is all done without any changes to the actual behavior of applications or any changes to how the user would interact with the system. So in Monad, the transactions are still linearly ordered. And the job of execution is to get to the end state of that long list of transactions as if those transactions just been run one after the other while strategically doing work in parallel and keeping track of like inputs and outputs and so on in order to make sure that we get the same result as if we had just run those transactions one after the other. Monad's approach is an optimistic parallel execution algorithm, meaning that many transactions are run in parallel, assuming that they're starting from all the same state and generating a bunch of pending results. Each of those pending results keeps track of the inputs and outputs for that transaction. And then we step through those transactions, those pending results one by one in the original order of the transactions and either commit that pending result if the inputs have not changed since the time of execution or rescheduling work in the event that one of the inputs has since changed. So in this way, there's assurance that we'll always produce the same result as if those transactions had just been run one after the other. I'll pause there to see if you had any questions about that.
Optimistic execution. That means that's a scenario where the transaction being executed, I think there is no conflict happening. But when things happen in parallel and a global mutable state, there's a lot going on. And is it possible that there could be a lot of conflicts happening because of this, like a global mutable state also trying to execute things in parallel there?
Mm-hmm. That's a great question. So maybe I can answer your question with an example. So imagine that there's 3 transactions that we're running in parallel. And the first transaction prior to that, let's say that I have 1,000 USDC in my account. And then there's 3 transactions where the first one is me sending 100 USDC to you, Suraj. The second transaction is totally unrelated, like someone minting an NFT. And then the third transaction is me sending 100 USDC to some other person. Let's call them Alice. Okay, so we have these 3 transactions. In optimistic parallel execution, what will happen is we'll just run all 3 of those at the same time, assuming the same inputs. For example, the first transaction will have an input of 1,000 USDC for me, and then an output of 900 USDC because I had 100 to send to you. And then transaction 2, ignore that. Transaction 3, it'll also have an input of 1,000 USDC for me and an output of 900 because it's starting from literally the same point in time as the first. All 3 of those transactions started from the same point in time. So we'll generate these 3 pending results. Again, the pending results keep track of the inputs and outputs, and then we step through and try to commit them. So we'll get to the first transaction and successfully commit it. we'll commit the second transaction successfully. And then when we get to the third one, we'll notice as we're trying to commit it, we notice that the input has since changed because now it's 900. So that means that pending result has been invalidated and that transaction needs to be re-executed. So then immediately we'll not commit anything else and go re-execute. And when we re-execute, the input for my USDC account is 900 and the output is 800. So we generate that new pending result, which is now correct, commit that, and then keep moving onward. So I just want to point out that because of this algorithm, we're always assured to be producing the same results as if those transactions had been stepped through one by one. And every transaction is executed at most twice. It's executed that first time in parallel, and then it may or may not be executed a second time in the commitment of pending results.
So, what are the other optimizations that uh, could you go into the details of the other optimizations?
Sure. The second one I want to mention is MonadDB, which is high performance state access. So the thing that you should know about transaction execution in general is that it's a problem that is IO bound rather than CPU bound. Like most of the constraints are actually due to having to read state from SSD. And that's a pretty expensive process because, the latency of doing one SSD read is somewhere between 40 and 100 microseconds.
Mhm.
And in existing Ethereum clients and EVM compatible blockchain clients, generally that state is stored quite inefficiently because it's stored using a high level key value store like LevelDB or RocksDB as the underlying data store, and that's being treated like a black box, and then the Merkle tree is being embedded inside of that other database. So when having to look up values from the Merkle tree, frequently those usages are having to query the database many times just to look up one value because they're navigating through the Merkle tree and then navigating through another tree structure under the hood that LevelDB or RocksDB or other databases use. So that's a backdrop of where one of the big constraints is. And with Monad, we built a custom state store for storing all of this state data, which natively stores Merkle tree data on SSD, and allows Monad to really leverage the power of SSDs much more effectively. Because the other thing you should know is that SSDs are actually extremely powerful. They've gotten really powerful over the past couple of years and continue to improve. And the areas where they improve are the number of operations per second that can be done, what's referred to as IOPS, and
Mhm.
then storage as well. For example, a 2 terabyte high quality NVMe SSD costs about $200 right now, which is really cheap. It's a lot of storage and it's quite fast at 40 to 100 microseconds. And it has a lot of IOPS, like for a high quality one, about 1 million IOPS. However, in order to take advantage of those capabilities of the hardware, we need software that can saturate that actual bandwidth and make many requests in parallel, read a lot of state from disk in parallel. And that's only possible by exploiting knowledge of the data structure that's being stored, i.e., the Ethereum Merkle tree. And so with MonadDB, we're natively storing Merkle tree data on this SD and taking advantage of the full throughput and capabilities of an SD.
Fantastic. Is it possible for Ethereum to adopt some of these changes? Because I saw a tweet from Vitalik about Merkle trees, and eventually this statelessness of Merkle trees will be leveraged by Ethereum. And that was a message, at least from that tweet that I understood. And you have already made this Merkle tree based structure, like a database, more efficient. What's your take on that, actually?
Yeah, I think that Merkle trees are interesting. I think the motivation for Merkle trees is ultimately so maybe actually just to take a step back. So right now, Ethereum has about 10,000 nodes that are participating in consensus, but the actual official validator count is more on the order of 1 million validators. But it's because one node can run many quote unquote validators on the same machine. It's about 1 million signatures whenever there's like a signature aggregation, which is a huge number of nodes, and a huge number of validators, which is a
Yes.
testament to the strength of the Ethereum block production environment, but it's also pretty heavy. And one of the longer term goals for Ethereum is to make it so that nodes can participate in consensus without having to execute all the transactions and without basically having to be a full node. So a full node in Ethereum is a node which maintains all of the state and executes all the transactions. And you can see that those two things are tied together because if you want to have all of the state, then you need to be applying all the incremental updates in every single block. And you also couldn't apply the incremental updates in each block without having all the state because each transaction depends on some of the state and you don't know what it depends on. So you need to have all of it. So there's a goal for nodes to be able to participate in consensus, like I guess to be able to vote on whether a block is valid without having to execute all of the transactions. But in order to do that means that each of those nodes needs to have access to all of the staking balances of all of the other nodes, like basically to know which validator signatures have stake associated with them. And normally the way to do that would be to have all of the state because then you could just go look at what all the balances that were staked are. And so I guess there's this hope that we could make it so that nodes could participate in consensus without having to have all of the state. But that means that then they would have to query other nodes for that state. And if they just query without asking for a Merkle proof, like if they just ask one of their neighbors, hey, what's the balance of so and so? Is it true that he's actually staking? Then the other node could lie. And so, in order to be sure that the responding node is not lying, we need the responding node to provide a proof. So, in Ethereum, because all the state is stored in Merkle trees, the proof would be a Merkle proof. And Merkle proofs are pretty big right now because they have to provide a traversal from the Merkle root all the way down to that individual node that, for example, is storing a balance that's being staked. And at each level of the Merkle tree, one has to provide all of the siblings of all of that node. So a Merkle proof, I don't know the exact size. I can probably find out, but it is quite big. And then a validating node would also have to ask for Merkle proofs for a bunch of different nodes in order to be sure about the balances of everyone. So, in other words, it's like this Merkle proof system is too heavyweight. And the idea of introducing Verkle trees and storing all of the state in the Verkle tree is that it offers lighter weight proofs so that then this dream of having nodes that are participating in consensus without having all of the state could be realized. But it's a very technical reason for wanting that. And the other issue is that the Verkle tree, although it offers smaller proofs, the downside is that it's much more work to maintain the Verkle tree. Like anytime you update a node and then you want to update all of the commitments in the nodes above, there's a lot more computation that needs to be done. So I think ultimately the trade-off between Merkle trees and Verkle trees is going to be one where the Ethereum community has to weigh the pros and cons of those. And I'm personally not convinced that the trade-off ultimately will be in favor of Verkle trees because the additional cost of maintaining those Verkle trees is huge. Again, I don't have the exact numbers on me, but it's much, much, much more overhead than maintaining a Merkle tree. And so as a result, it might actually be trading off. The cost might be too high. It might not actually be worth it to do this initiative, in addition to the fact that there has to be this huge migration that happens to move all of the state from the Merkle tree to the Verkle tree, which is going to be a big mess as well.
And you have already managed to make it more efficient, the database, the state access more efficient.
Yeah, exactly. Monad has done it for Merkle trees, but not for Verkle trees. So that would be yet another vote in the column of keeping the Merkle tree around.
Exactly. So theoretically, Ethereum could adapt these changes that Monad has innovated on and maybe push this trend. The push for Verkle trees could be, but there may not be that need. That's
a good point, because one of the motivations of the overall Verkle tree effort is to make it so that it's easier for nodes that are participating in consensus to maintain all. It's trying to make it so that they avoid having to maintain all the state, but the other way to do it is to make it cheaper to maintain all of the state. and MonadDB does that.
Yeah, exactly. And what's the third main optimization that Monad has achieved?
The third main optimization is asynchronous execution.
Could you elaborate on the idea of asynchronous execution?
Sure thing. Asynchronous execution is the idea of maintaining basically separate swim lanes for consensus and execution. Maybe to start, I just want to give a simple factoid, which is that in Ethereum, the blocks are every 12 seconds, but the rough budget for execution is about 100 milliseconds, which is
Mm.
less than 1% of that total block time. So it's
Right.
a pretty crazy situation where, the movie Limitless, where the premise is that people say that you only use 10% of your brain, but then in this movie, this guy takes a drug where he can use 100% of his brain and he becomes a super genius. He's able to like solve all these problems. And of course, more problems come with that. But
Yeah.
yeah, so that's the point here is that right now in interleaved systems where execution is a prerequisite to consensus, it is the case that only a small fraction of the block time can be allocated to execution. So in Monad, the nodes come to consensus on the official ordering of transactions without executing. And then after the consensus on that block and that official ordering is agreed upon, then two things happen in parallel. One is that you start doing consensus on the next block, and the other is that they go execute that list of transactions that they just agreed upon. And so as a result, budget for execution can become 100% of the block time instead of only a small fraction of the block time.
So what kind of improvement? So that from 1%, like a theoretical is becoming 100%. Or you're saying that is like a 100x improvement in that particular optimization. That's pretty crazy, actually. How exactly are you achieving that?
In existing systems, there is this notion of state machine replication where the nodes, in addition to like a block proposal, has a list of transactions, but it also has the Merkle root post those transactions. So it's a requirement that the leader has executed that list of transactions already. It's a requirement that all the other nodes that are hearing that proposal and executing those transactions also do so and get the Merkle root and compare it before voting. Whereas in Monad, that Merkle root is moved out of it's not required that the nodes have executed prior to coming to consensus. And instead, there are some other changes made to the protocol in order to defend against a couple of possible concerns that one might have with this paradigm where the nodes aren't executing prior to consensus. And the specifically the concerns that one might have are spam protection. So you want to make sure that because the nodes are coming to consensus with a slightly delayed view of the state, that it's not possible for someone to basically empty their balance and then send a bunch of spam transactions from that balance. That's one thing. And then the other thing is making sure that the nodes, because they're all executing independently, still adding a safeguard to make sure that the nodes are still ultimately getting to the same result, which is done through the introduction of a delayed Merkle root. The Merkle root from roughly 10 blocks ago is the one that's included in consensus. So if one of the nodes gets hit by cosmic rays and has an error of some sort, then that'll be identified at the point in time of consensus, and then that one node will go and re-execute those 10 blocks.
What is the fourth main optimization that you're also making?
Yeah, basically up to now, most of the improvements that I've been talking about are very execution related. They're related to allowing the system to process many more transactions than otherwise was possible before. But a blockchain is both consensus and execution. And you need both systems to be running at high capacity in order to have a blockchain that can process a lot of transactions. So the fourth and final improvement is actually a really big, like overarching improvement of building a really high performance consensus mechanism that can keep up with the execution capabilities of Monad. So in Monad's case, we use pipelined two-phase hot stuff. So this is an algorithm that's originally based on the hot stuff consensus mechanism, which is a linear communication complexity algorithm, as contrasted with Tendermint, which is quadratic, and with additional research improvements that have additional efficiencies for hot stuff, ultimately allowing the system to scale to several hundred nodes that are participating in consensus while having fast block times of 1 second and having single slot finality.
Oh, yeah. That is, I think, very important part in the sense that one of the main problems because of the messaging overhead, 100-ish is the kind of maximum number of nodes that can participate in that system. And from a decentralization point of view, from at least from the way Ethereum community sees it, the maximizing decentralization is part of it, and 100 nodes is limiting. But in Monad's case, you can actually achieve several hundreds of nodes participating in the consensus at the same time without affecting the performance.
Correct. I think that a lot of Tendermint chains end up capping out at about 100 nodes because the communication complexity is quadratic. Because every node is messaging to every other node. That means every time you add another node, now you're adding n more messages. Whereas with hot stuff, it's a linear communication complexity algorithm in the happy path, like in the normal case. So a leader just sends messages directly to all the other validating nodes, and the validating nodes send their votes directly to the next leader, who then aggregates those votes into something called a quorum certificate, which is an aggregation of all those signatures attesting to that previous block proposal. And then that leader can send that quorum certificate out to all the nodes directly. So because of this direct, like one to many to one communication, it's just much less overhead from a communication perspective. So it's much easier to scale the network to hundreds and ultimately thousands of nodes.
Even thousands. So in that sense, consensus won't be a limiting factor in the number of nodes which can participate in the system from your perspective.
That's my expectation. Yeah. I do think that actually consensus, it will be the limiting factor for the overall TPS, overall throughput of the blockchain, just because you can't fight against the laws of physics. Like if we want a fully geographically decentralized network with nodes that are anywhere in the world, then literally like the amount of time it takes to go from one side of the world to the other is 100-ish milliseconds. It's just literally going to be the case that the block time can't go below a certain amount. But from a number of nodes perspective, that is an area where there can be continued improvements, efficiency gains to scale to 1,000+ nodes.
And from a user perspective, I think as of now, Ethereum, at least last year, the total amount of fees paid in the Ethereum L1 was around 3 billion. And it's around 1 million transactions per day. And it's around then 360 million transactions. So it adds up to around $10 to $15 per transaction. So I don't think that 80% of the world can afford that. From a user perspective, what will be the like average transaction fees on Monad? And from a developer perspective, now you can see that pretty much the dApps on Ethereum layer 1 is pretty much the market is pretty much mature, it's established. So when Monad brings in such EVM with much more capabilities, what kind of innovations do you anticipate? Is there something that you are seeing in your DevNet and or something that you think that could happen, like people would try different stuff?
I think that, yeah, like you said, even stronger than what you said, basically no one can afford $10 to $15 transactions. There's some people that are like really OG Ethereum people that have a huge amount of Ether and they're okay with paying that. Or their transaction size, like the amount of notional being traded, makes it so that $15 gas fee is small compared to the cost or compared to the overall notional size. But like normal everyday people hate paying $3 ATM fees. Like you're not going to want to pay $10 just to like swap on Uniswap or deposit into Aave or pick up an item in a game. So there's clearly the Ethereum L1 fees are too high, and I think everyone understands that. But it's also true that Ethereum layer 2 fees are too high for most purposes where you're aspiring to any semblance of mass user adoption as a developer. Like if you're a developer outside of the Web3 space, you're building a mobile app, your goal is to be number one in the iOS App Store. And that means getting to hundreds of thousands or millions of daily active users. And so if you do the math where it's, if I have 1 million DAUs, people are transacting 50 times per user per day, that's going to be 50 million transactions per day, which is 500 TPS. And no environment can support that right now, maybe with the exception of Solana. So Monad is offering that Solana-like experience while having full bytecode compatibility for EVM so that developers can build in the portable language that they're used to. But yeah, I think from a fee perspective, Monad is, if you think of the waterfall, it's like $10 for an Ethereum transaction or 10 cents for an Ethereum layer 2 transaction. A tenth of a cent for a Monad transaction is our expectation for a simple Uni V2 swap. And so it's 100x reduction from layer 1 to layer 2, but it's another 100x reduction from layer 2 to Monad.
I can totally see that why people would prefer to use system. It's a straightforward case. There's one more reason where people tried and developed different kind of systems, like move VM, for example. It's one of the reasons is because of there are like a lot of hacks often happen on the EVM side of systems, and people try to make it more secure. So, what is your take on that? The security part, like sometimes auditing is just a process, but it doesn't bring that much. If you look at the Kyber swap event, it's a very low probability event that happened. So from a security perspective, what's your take on that?
Yeah, I think that security is extremely important in Web3. And one thing that Monad is doing to help improve security is by changing the trade off between the cost of additional code and the security that comes from additional defensive assertions in the code. For example, with Uniswap, there's this invariant property that's always supposed to be maintained, which is that X, which is the number of quantity of asset one, and then times Y, which is the quantity of asset two, is always supposed to be equal to K, some constant. Actually, the K is even increasing a little bit because of the fees that are being paid to the pool. So there really should, this is an invariant that should always be true. And you could imagine, like when writing the Uniswap code, you would just want to litter this invariant throughout your code to make sure that it's always being, that invariant is always maintained. And right now, when coding that, you wouldn't want to just add all those defensive assertions because it's going to cost more gas. And already, like, users are paying $10 per swap on average. So you don't want them to pay like $12 or $15. But in Monad, by substantially reducing the cost of each of those computations, we're making it so that developers aren't faced with this very difficult trade-off between complexity of the computation and the cost, and ultimately allowing them to express all of the defensive assertions that are needed to protect the protocol without incurring significant cost.
So in effect, devs would be able to code a much more secure app that they would choose to code in Ethereum L1, for example, or in
That's
L2.
correct.
What is the grand vision of Monad? So is Monad also will be looking at eventually having L2s? Because eventually for L1, never be enough to accommodate the whole amount of transactions or the possibility of how Web3 would expand, and one L1 won't be able to accommodate that. So what is that grand vision of Monad?
Yeah. Monad is extremely focused on optimizing the performance of a layer one blockchain by making fundamental improvements to the execution and consensus stack to get the most performance out of commodity hardware. The goal is really to write new software, make new algorithmic improvements that get as much as possible, like squeeze as much performance as possible out of the hardware. Ultimately, I agree with you that there are fundamental constraints to how much one layer one can scale. But I think given the current landscape of blockchains, we're definitely not there yet. Monad will, the goal is to saturate the capabilities of the hardware and basically make networks that are much more computationally dense so that one blockchain network is offering well over 10,000 transactions per second of throughput or a billion transactions per day. And then at that point, if there's a need for multiple billions of transactions per day, which I do believe will happen at some point, then there's always potential for horizontal scaling for multiple Monad instances that each are processing a billion transactions per day, maybe focused on some specific vertical or some specific ecosystem. Like you could imagine an ecosystem just centered around one particular game, and then all of the shops and customization applications and so on that are all tied to that one game. But fundamentally, what's needed is much more dense much more computationally dense networks, and then we can start horizontal scaling as we need to.
Oh, yeah, great. And finally, what's the next upcoming update of Monad? I heard about the DevNet news. What about like the public testnet or Mainnet? Is there anything that you can say about that?
Yeah, the next steps are opening up the DevNet to individual developers on a one-by-one basis, which will happen gradually, and then gradually opening it up to the point where it is a public test net. That's really the short-term roadmap, and then beyond that, continuing to iterate, continuing to load test in preparation for the main net.
Okay, fantastic. That was fantastic conversation, Keone, and thank you for taking the time to go into those details and explaining all of that. I would say it was an eye opener for me to what could be done on the Ethereum EVM side. People thought that it's like saturated what people could do, but the Monad team has proved that there's a lot more space for improvement, and you can bring in a lot of innovation there. And you have already done a fantastic job. So I'm really looking forward to the next steps that Monad is taking, and looking forward to the mainnet. And yeah, thank you again for being here.
Of course. Yeah. Thank you so much for having me.
Thanks for tuning in. If you are keen on getting deeper insights about Web3 tech, our newsletter, Just the Metrics, is just what you need. It's packed with valuable information and it's completely free. You can subscribe by clicking the link in the video description. It's a great way to keep up with the latest in the Web3 space straight to your inbox. And before you go, please hit that like button and don't forget to subscribe to our channel for more updates and insights. Your support is what keeps these videos coming. So see you in the next video.